All right, in this video we're going to talk about greatest common factor, least common multiple, the Fibonacci sequence, and the golden ratio. And then we'll finish it off with a little bit of modular arithmetic, which will finish out this section of our course. So the greatest common factor is the largest factor that goes in a set of numbers. So for example, if we have the numbers 32 and 56, scroll over here a little bit, and I build a prime tree, right? So 32 is 8 times 4, and 56 is 7 times 8. And so if I keep breaking this down, because I got to make sure, I mean, 8's the answer. You might see that already, but I want to show you why. Because this breaks down to 2 to the third power, because 2 times 2 times 2, and this is 2 squared. And 7's a prime, and this again is 2 to the third power. So choose all the prime number using the one with the largest exponent. Right? And so 2 to the third power is the highest one that they both have in common. So it is their greatest common factor. For least common multiple, you're going to find the smallest number that is a multiple of the set of natural numbers. So if we have 54 and 30, if I, I'll write it this way, 30. What I usually do is I start with the smallest number and write out its factors. So 30, 60, 90, 120, 150, 180, let's see, 210, 240, 270. All right, and dot, 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 you can keep going. After I get quite a few written out, then I start doing 54. So 54's first one is 54, and then 54 times 2 is 108. And then 54 times 3, 162. And then another 54 is 216. And then another 54 is 270. And 270 and 270 are the first number they both can go into. So that is least common multiple. Now, in the reading, there's a bunch of different ways to do this. I'm showing you one of the ways. So a Fibonacci sequence is a first set of numbers is basically a pattern, right? And so the way it works is this, if this is the first set of the value, right? Oh, don't want highlight, I don't want a pen. First set of the value, so we'll call this f sub 0. And then this is f sub 1. Well, the way it works, the sequence is, if I add the first two together, 1 plus 1 equals 2, which is where the 2 comes from. And then this is this second. Now, those is the third number because we start at 0, right? So then if I add 2 plus its previous 1, I get 3. And then if I take 3 and I add its second number, I get 5. And I can keep doing this. I take 5 and I add its previous number, I get 8, and so on and so on. And there is kind of the pattern. There, I put a video on the playlist that goes into great history of it, but that is the sequence. And so if I take any two numbers, say 55 and 34, and I divide them, so 55 divided by 34 equals 1.617. Then let's take another set. We'll do 233 divided by 144. So 233 divided by 144. And I'm just putting this in a calculator. I get 1.618. And a lot more decimals. So these are known as the golden ratio. The golden ratio is two Fibonacci sequence numbers divided in ratio from the largest over the smallest, and it creates this. And then, because it is a irrational number, because it goes on forever, they figured out the golden ratio to be 1 plus the square root of 5 divided by 2. Now, if you put this in your calculator, be careful. I would put this in parentheses if you do not have a fraction key that looks either like this on your calculator or n over d, something like that. That will let you put it in that exact form. But if you are using the divide key, make sure you put parentheses to get this number. Some of the homework problems I have when you calculate the Fibonacci sequence. Again, if you want to get way more information on the usefulness of this and the patterns of it, please watch the video I added, not created by me. He does a really good job of explaining these sequences. Last thing we'll talk about is modular arithmetic. So I have a Word document here. Oh, draw. There we go. Open in Word. Not now. All right. Oh, I love my iPad sometimes. I just had this open so this would not happen, and I think it just froze. There we go. So modular or clock arithmetic is essentially used in cryptography and computer science. Why are a lot of you taking this class? So we'll kind of look at how it works with the clock. A modular formula is written as A, the 3 lines, B mod n, where A and B have the same remainder when they're divided by n. So if I divide A by n and B by n, I should get the same remainder, right? So using the rest of the we can see that 10 and 3, because 10 and 3 have the same remainder 3 when divided by 7, right? So I'll do a couple of these, and he goes into how to do addition, subtraction, multiplication, and some remainders, and solve in modular arithmetic applications. So a good read. So what we'll do here is we'll go back to our notes, and I'll do a couple of examples here. So if we do it with a clock, right? So military time is how I understand it, or it's a 24-hour clock, right? So if it's 13:27, we've gone past the 12 o'clock noon time, so we are now in the afternoon. So if I subtract 12 from this, I get 1:27, so it is 1:27 p.m. in the 12-hour clock. So this is the 24-hour, and this is the 12-hour. And then we can add things together to do the clock, right? So if it's 8 o'clock, and I add 12 hours to it, I get 20 o'clock. So 2,000 hours, or 8 o'clock p.m., assuming this is a.m. I can also multiply things. So if I do, and again, based on the clock right now, and then we'll do some modular stuff. So if I do 5 times 6, that gives me 30. Well, I've gone past the 24-hour day, so I do 30 minus 24, which gives me 6. And then finally, we could do by minute. So if I do 10:55 and I add 1355, I will get 5 and 5 is 10, carry the 1, 10, 11, carry the 1, 2410, right? Well, again, I've gone past the clock. So if I subtract out, I've gone 10 minutes past the hour. So that would be 0010. Let's do one more. So say I have 945 and I add 1450 to it. So I get 5, 9, 9 and 4 is 13, carry 1, 2395. Now this is a good example because notice I'm in minutes. I've gone too far past 60 minutes, right? So if I subtract 60 for an hour, then this becomes 24 because I add it to this, my 1 hour, and I'm left with 35. Now again, I'm past the 24-hour time period, so this becomes, because we don't write 2400, our clock start at 00, so this is 0035 or 35 minutes past midnight. So there's some time examples. So let's look at some different ways of solving modular. Right? So let's prove that A, B, mod n. So we have 13 equal mod 6. So not mod 6, mod 7. So the way I do these is I take and use the concept of A. I'm on my clock again. A divided by M should have, not or equals B, a remainder of B. So, if I'm doing this problem, I would take 13 and divide it by 7. So 7 goes into 13 once. So 1 times 7 is 7. I subtract, I get 6. So this equals my remainder, which is exactly, which is right there. So this is a true statement. Sometimes what might happen is we will get a problem where, I'm sorry, I'm looking for my notes. There we go. When the number's too big. So in other words, if I have 47 equals 77 mod 7. Remember, this is supposed to be our remainder, right? And so only you can have a remainder if it's less than the mod value. So what you can do is you subtract these. So 77 minus 47 equals 30. And then I divide 7 into 30. So 7 going to 34 times, 28. Subtract 2. It doesn't go in evenly. So therefore, it's not, it's not true. So this is false. Also, if we do 7 into 47, so 7 into 47 is 6 times. That's 42. And you subtract, and you subtract, and you get a positive 5. And if I do 7 into 77, well, that goes in perfectly 11 times with a remainder of 0. So again, not true. We can add things together. So example 3, I can do 79 plus 56 mod 7. equals blank mod 7. So I want you to find the missing piece. So I add 79 and 56 together, I get 135. And I divide it by 7. So 7 goes into 13 once. I subtract these, I get 6, 5, and then 9 times is 63. And I have a remainder of 2. So that value is what I put in the box. Because remember, the nav in front of the mod can be reduced down. If I subtract them, 39 minus 55 mod 6, and I want to find the missing piece, mod 6. Well, 39 minus 55 gives me a negative 16. So then what I do is I divide this by 6. And because it's negative, I'm going to put a negative 2 up here. So that gives me a negative 12. However, when I subtract these, that becomes positive. So I get a negative 4. So you got to remember your long division rules. Right, but I can't have a negative number in there. So what I do is I just subtract that from that. So 6 minus 4, again, is 2. So that is 2. And then lastly, we can multiply them. So if I do 12 times 11 equals blank mod 6. It doesn't always have to be mod 6, as my examples are. So 12 times 11 is 132. Right. I divide this into 6. So 6 goes into 13 twice for 12. I subtract 12. And again, it goes in twice with a remainder of 0. So I just put a 0 there. I also attached a nice video of explaining modular arithmetic, not again created by me, that goes in a little more detail. So these are some examples of how to solve them. Use these other videos to go kind of more into the theory if that is something that interests you. And this finishes out our chapter 5. And then we'll move on to another lesson next week. Thank you.